So far, we discussed about the descriptive statistics, and also we took a digression and we jumped into Python. You learned Python or the intermediary level. Next, we will take a look at the inferential statistics. So what is inferential statistics? And what is descriptive statistics? What is descriptive statistics? So the descriptive statistics focused on summarizing the key features of a data set, or it gives us the gist of the features of the data set. Somebody has given you data, sample data, or some data they've given you. With that data, you can apply the 5-number summary. What is the 5-number summary? Minimum, maximum, quartile 1, quartile 3, and median. Probably you can use standard deviation also in addition to that, and also you can use coefficient of variation, right? So those kind of measures you can apply. With that, you can give us the summary information about the data. So with that, we should be able to gain a quick insight, irrespective of the volume of the sample data or so, we'll be able to understand quickly. Whereas the inferential statistics, it focuses mainly on making generalizations about a larger population based on a representative sample of that population. In the case of inferential statistics, we work with sample only. Remember this. Because in real time, we don't get population data. Even if you get population data, it is time consuming. Okay. We cannot use the population data. It is not wise to use the population data. Most of the cases, we work with sample data. The number one reason is the volume of the data is very high. Population data, hence you cannot use it. The second reason is it is not accessible most of the time. Even if it is accessible, let's say I work with Walmart, I work with Target. Okay, the data is already available in Hadoop cluster. The data warehouse, 5 years data, 10 years data is there. Then how can I say that I don't have the data? Data is available, but to pull the data and do the analytics, it takes a lot of time. Right, so hence we will be using the sample of the population, and if you use the sample of the population, that is more than sufficient. Okay, so that is more than, so we don't have to have the entire population data, and even if you pull the population data and if you try to generalize something right, it will take a lot of time. So now the question is, what about the accuracy? When I try to take a sample or representative, let's say, I'm taking a sample which is a representative of my population. With that, when I try to generate my population, how accurate? Okay, see, the accuracy is the accuracy of your inferential statistics. It relies completely on the sample data being both accurate and representative of large population. Okay, so your sample is supposed to be random and it should be a representative of your larger population. Okay, and if your sample sizes are bigger, it is good. Okay. Okay, fine. So that is what at a high level you need to remember this. Okay, so now what we will do is we will see what we can do with the inferential statistics. We can make an inference about the population using inference statistics. We can make an inference about the population. The ultimate objective of the inference statistics is to use sample data. Instead of saying a sample data, random sample data with representative of your population data. If you use it, you can estimate the unknown characteristics of your larger population. Okay, and also the inference statistics, it uses probability to analyze the sample from a specific population or to improve our knowledge about the population. The probability, you can predict the probability. What is the probability that tomorrow it will rain? Is it 0.5 or 0.6? Higher the probability, the higher the likelihood that it can happen. So lesser the probability, lesser the chances that you will get promoted. For example, the chances of me getting promoted in this appraisal cycle is 0.4, which means the 0.4 is closer to 0. See, the probability values are lies between 0 and 1. 0 and 1. See, in practice, in plain English, we use percentage to, to specify or quantify the likelihood of an event occurs, right? So, so there is a 40% chance that I can get a promotion. There is a 80% chance that I can get a promotion in this appraisal cycle. We use percentage, but when it comes to statistics, we quantify the uncertainty using the probability. The probability values ranges between 0 and 1. And also, it is not wise taking the entire population data to make an inference. Okay. So instead, what we do is we use the sample data that is more than sufficient to generalize your population. Before we dive into the inferential statistics, let us understand certain terms. Okay, we know what is mean, all these things, right? So mean, standard deviation, variance size, and anyhow, I'm not going to talk about proportion, correlation, you know very well. So for a sample, and you know what is sample, what is a population. For a sample, if you want to find out the mean for a sample or the average, we use a notation called X bar. For the population average, we use a notation called mu. And for a sample standard deviation, we use small s, and sigma is for population standard deviation. Variance, s squared and sigma squared. The square of s squared and square root of sigma squared is your standard deviation. And size, sample size, we use a notation called small n, whereas here we use capital N. And proportion, p and pi. Correlation, we for a sample, we use a correlation notation as R and P. But at this moment, if you remember these three or four, right, that is more than sufficient. Now, if somebody is asking you what is the difference between descriptive and inferential statistics, so take a look at this data set. This is a sample given to you. With this, you can quickly give descriptive information about this data. Okay, your discussion, the descriptive question could be asked about this data, like, what is the common age of frequent shoppers in Orange County. This data is related to Orange County. In USA, you have something called Orange County. A county is something like one specific area, okay, in a city. So in a city can have more than one county. So a city is, let's assume that in this case, it is a population and subset of them is your county. So this is the data you have it. If somebody is asking what is the common age of frequent shoppers in Orange City, here the FS stands for frequent shoppers. New stands for, the new customers, one-time visitor, and price sensitive customer. This customer is very particular with the price. These guys are frequent shoppers. What is the average age of the frequent shopper? You can tell quickly, for example, if this is also 26, right? You can say on an average, approximate the average age of frequent shopper is 28 or 27. So this is the descriptive question. If I ask you an inferential question, okay, are the ages of frequent shoppers, in this sample similar to what you would expect in the entire people, those live in Orange County? See, within the Orange County, they've given the sample data. Even this is not the entire Orange County data. Okay, within this average, the Orange County sample data, they've given 3, 6, or 7 randomly. They sampled it and they gave this data to us. Okay, and if they ask you what is what is the descriptive question, like what is the average age of frequent shoppers, you can see 26 or somewhere 26 or 27, right? You can say that way. Does that mean the entire population who live in Orange County, their average, the average age of the frequent shopper is same as the sample average age? Can I say like that? Say yes or no. If I draw another sample in the Orange County, let's say in the Orange County, let's say close to 3,000 people are there, households are there. Okay, this is just, let's say 1,000 people are there. This is just 7 people. I randomly ran a survey and we noted down. Okay, and when I run another sample survey, That survey, the data could be different. Maybe in that data, the frequent shoppers age may not be, the average age may not be same as this sample's average age. Sample to sample, it will vary. So can I generalize with this sample data? All the frequent shoppers average age is 28 in average county. Can I do that? Can I do that in inferential statistics? Inferential statistics, it gives you about the statistics about this data, this given data. But I don't know the average age of frequent shopper for the unknown universe. In this case, the universe is the county, that is the population. So is it possible to infer based on the given sample? Can I infer the population? That is possible with inferential statistics, whereas that is not possible with descriptive statistics. Just descriptive statistics will tell us what is the minimum age of the customer, what is the maximum age of the customer, what is the average age of the customer, standard deviation tells us. Whereas with the given data, you cannot, using descriptive strategy, you cannot generalize the population, the average age of the frequent shoppers, because the population is unknown characteristics. We do not know, right? So when you take another sample with a little more data, sample to sample, it will vary. So the descriptive statistics is unlike inferential statistics, seeks to describe the sample data, which one the descriptive, but it does not, or it do not attempt to make inference from the sample to the whole population. Sample to population, you cannot make the, this is my sample, with the sample itself, we cannot make inferences about my population. Okay, for example, let's take another example. A manufacturer, right? So before launching a new car washing powder. So let's say a manufacturer wants to launch a car washing powder. They want to run a survey with the car owners to find out how frequently the car owners clean their car, with an intention of identifying the attitudes of the car owners and knowing customers' likely response to buy their product. Simple. See, I want to launch a car washing powder. What I do is I go to ADR and I randomly run a survey with a few apartment people. And based on their attitude, can I generalize all the people in ADR? They wash the car on a daily basis using car cleaning powder. No, right? So in this case, we have randomly ran a survey with 250 car owners. Now this manufacturing company, they selected a random sample of 250 car owners and interviewed. Okay, so by applying descriptive statistics, maybe you can say on an average 12 times a year, the car owners wash their car using the car cleaning powder. So which means every month, monthly once, they use the car cleaning powder. And right, so per month, right? So on an average, okay. And for for the 250 car owners whom I ran the survey, so I got to know with the help of this descriptive strategy that each month, monthly once, they use the car cleaning, and only 7% of the car owners regularly used car cleaning product to wash their car. Right, so with this, we can give this much of information. But using the inferential statistics with a sample of 250 car owners, can we estimate and hypothesize the, let's say, the likely response profiles of all car owners are able to, let you know, we can say there is a 95% that car owners wash their cars on average between 7 to 10 times per year. Right, so with the, right, so with and also at the 5% level of significance, there is insufficient sample evidence to 20% of all cars use car body wash products regularly. It is a 95% chance that, no, if it is, that means the remaining 5% that right, so we don't have sufficient sample to conclude that the 25% of all car owners use car body washes. So what do we conclude here? So using descriptive statistics, we can describe or summarize the data and present the same in charts and tables. To generalize from samples to populations, we can use inferential statistics. To draw conclusions, we use hypothesis testing as part of inferential statistics. And also we can find out the relationship amongst the variables, and we can make predictions using inferential statistics. In inferential statistics, we can go one step further. Just by giving the numbers, on an average 12 times per year, the car was there. That doesn't mean, all the car owners in this population, right? So monthly they will buy only one car cleaning product. We cannot generalize, but with the help of a confidence interval or hypothesis test as part of inferential statistics that are available, we can make a generalization. That is the difference between descriptive and inferential statistics. Okay, so any questions so far? Okay, next what we will do is we will jump into understand the samples. First of all, let us take a look at what exactly the sample is all about. What is population and what is sampling distribution? All these things we will take a look at it, so that you will get to know how you can so what is the basis for your sampling, right? So the basis for your sampling, right? So just because I can use inferential statistics techniques like the hypothesis test or confidential interval, I can generalize the population based on the available data, right? Sample data, I can do it. First of all, you should be knowing what is sample, what are the different types of sampling techniques are available, how do you need to sample that. Okay, so that is the thing, you should be knowing it. So what is population? Before we go ahead and understand the different techniques that are available to draw the samples, right? First, let us understand what is population. What is a population? Population is you, me, and everyone in Chennai. This is a population. Or we can say the entire people in India is a population, or all the people in the globe, we can say it's a population. Population is also called as universe. So the population can refer to people, or it can refer to buildings, businesses, motor vehicles, events, so on and so forth. Okay. Now the question is, what is the need to know who or what are in a population? It depends on what kind of test that you are planning to conduct. See, often researchers want to know things about population, but do not have data for every person or thing in the population. For example, if a company's customer service division wanted to learn whether it is mobile phone customers are satisfied or not, in order to know this, they need to know that if they have mobile phone population data, okay, so that they can contact mobile phone users. So those people do not use mobile phone at all, right? So what is the point in contacting them? So you need to make sure that your population, consists of the mobile phone users. But it would not be possible or practical to contact every individual who purchased mobile phone, right? So instead, what the company do is they might select a sample of the population. Okay, they might collect the sample of the population. These are the examples for the population. All the female digital buyers in the world, all the teens own laptop in the world, population of all employees in a company. And so these are the example for the population. The sample is a subset of your population. That's it. So it's a small subset of population. Okay. So now the question is it possible to measure the height of all the males in the globe? Is it possible? It is not possible, right? Highly impossible. Because in the world, all the people in the world, the height it's not possible. So that's the reason why we need to do sampling. So sample is a subset of the population. In most of the cases, gathering information from the entire population is not always possible. It's not the data is not available. Even if it is available, right, due to barriers like time and cost, right? So one second, the time and cost are very high, and right, it's highly impossible. We can say highly impossible to collect the entire population data. Instead of gathering the information, the whole population, we often gather information from a smaller set of the population. That is called your sample. That is that. So that is what we call it as a sample. Okay. So is it possible to draw a sample from a population? Yes, it is pretty simple to take subset of the population, and then making inference about the population also pretty simple. So, okay, what is the, can I blindly go ahead and draw the sample? So what is the rule? Is there any rule that I should follow while extracting the sample from the population? The sample must be a representative of population. Please remember this. This is an important point. And the sample must be random. It should be unbiased. The sample should be unbiased and it should be representative of population. Okay, a lot of sampling techniques are available. The advantages of using sample is pretty straightforward. It can save cost and human and other resources cost, right? And disadvantage may not be representative. Researcher can only estimate that there is a degree of uncertainty if you sample the data just like that. So that's the reason why they came up with different sampling techniques. One is the probability based, other one is non-probability based. As part of probability based, we can see SRS, simple random sampling, and then other technique is stratified random sampling, cluster sampling, and systematic sampling. And there are some other techniques are there. We will see it later. Okay, and non-probabilities, convenience, and quota sampling. These two are biased. Okay, so in general, we don't go by non-probability convenience sampling based on your based on some number. You do quota sampling. That is not going to be helpful. We will start with understanding the commonly used sampling technique called SRS, simple random sampling. What is simple random sampling? Look at this is my population. In this population, so every item in this population, we choose it in such a way that every item has an equal chance of being selected. So if you see, I think most of you would have noticed this, right? In the TV show, they write the name of each person in a paper, and then they fold it, and then put it in a paper in a jar, and then they will call a small kid, and then they blindfold their eyes, and then ask the kid to put its hand and shuffle everything, and then take out the three folded papers. Why they close the eyes? Why they shuffle it? When they shuffle it, there is every possibility that every individual name is written in that chit, right? The folded chit, will have an equal chance of being selected. Randomly, you are closing your eyes, you are picking up blindly, right? Three. What is the advantage? It's unbiased. Since your eyes are closed, you are unbiased, right? And you are shuffling that. You're shuffling that, and then you are closing your eyes and picking up the things. Hence, it is unbiased. The disorder, it may not be representative. Since it is not representative, there will be a large variance. What do you mean by representative? Simple random sampling meets one requirement. What is the prerequisite to draw a sample? The sample must be unbiased. Since you are closing your eyes and yes, it is unbiased, but it is not representative. What do you mean by representative? Let's say you want to run a survey to understand the average amount spent by the population in a specific area. Let's say in Thiruvanmiyur in Chennai, we want to understand the average spent by all the people, those live in Thiruvanmiyur in Chennai. So in Thiruvanmir, what you do is you run a survey with all the people, those live in a posh area, rich people, high income group people, and some medium income group people. But you did not run a survey with the low income group people at all. Ideally, you should have ran a survey with rich and high income, medium income, low income group people. Randomly, you should have selected people from these three groups, and then you should have ran a survey. Since you ran a survey only with majority of the high income group people and few of the middle income group people, but you ignored the low income group people. Hence, it is not representative. Your sample is not, your sample should represent all the segment of the people in the population. So, but you closed, you randomly called, you did not call your relatives or friends. You randomly called some people and you ran a survey. Hence, it is unbiased, but it is not, there is no coverage. The right term is coverage. It is not covering all the three type of population or all the three type of segments, high, medium, low income group people. Hence, it is not, so there could be chances because you are closing your eyes and calling people, right? There could be chances you might not be in a position to call the low income group people. You just think that way, okay? So the next one is the simple stratified random sampling. Okay, this addresses the drawback of the simple random sampling, which were the stratified random sampling. This stratified random sampling ensures that every strata is called as a group, is represented proportionally. This means that a number selected for each group in a sample is in proportion to or reflects the relative size of different groups in population. Look here. In this population, three groups of people are there. Okay. And okay. And here, let us assume that, these three group peoples, they buy three different brands of mobile. Okay. And let's, in this group of people, they buy Samsung, and this group of people, they buy Redmi mobiles, and these people buy iPhones. In this case, if I wanted to sample, if I want a sample of 10, okay, we should select from each size proportionately. Okay, so how much I said here? 500. Remember that. So 300, 800 plus 200, 1000. So 1000 mobile phones. Right. So for every 1000 mobile phones sold by mobile store, 500 are Samsung, and you just think that way, 300 MI, and right. So if you want to do sample of, if you want to have a sample of 10, so we need to select from each size proportionately. So here 500. So out of 10, so my sample size is supposed to be 10. How much should I pick up from here? 5, 3, 2, right? 10. So 5 people, 5 mobile phones from Samsung, or let's say, the three groups of people, they buy always Samsung. These people, right, they buy only mobile Samsung. These people, they buy only MI. These people, they buy only iPhones. But if I wanted to sample the data with the size of 10, how should I sample it? All these segments, I need to randomly sample the data. And also I should make sure that I should select from each size proportionately, which means, so 5 plus 3, 8 plus 2, 10, right? My sample should have a mix of all these three segments of people, but it should be represent proportion to its relative size in population. Just give me a second. Okay, with proportional sample, the sample has proportion as the population. With proportional sample, the sample has proportions similar to the population proportion. This is how you need to randomly sample it. So in this case, the sample is randomly. See, in this case, we have randomly sampled the data, and also it represents all the three groups. Besides this, it represents proportionally to its relative size in population. This is how you need to draw the sample. The other cases, does that mean if I have the disproportional sample, right? Sometime every group is represented disproportionately to its population. For example, here I have 800, 600, 400, and 200. 800 Samsung, 600 MI, and 400 some other Vivo, and this is some other brand, 200. With the proportional itself, right? See here, we could see a lot of disproportion. If I want to draw 10 samples, in what proportion that you will sample it? Because every group is represented disproportionately. But if you see here, it is represented proportionally. 500, 300, and 200, 800, 1,000. Right? So there is a proportion, but here there is no proper proportion. So sample does not have the same proportions as the population. You can do it this way also. Your sample need not to have the same proportion as the population, especially when you have the disproportional data groups like this. Okay. So in that case, what you do is, here you can, let's here you can take 20% of the data. So 20 is how much? 400 is 50, and 200, and here you can take 10% or 10%. 10% is how much you'll get. Sorry, not 10%. You can take 20, 20, 20. Here you can take probably 50%, so that it will be more. Your sample will have, will have the equal. If you go by literally, right, the proportional, what will happen? So you will take, let's 100 samples. I want to draw it. So 80 here, and let's 60 here, 140, 200 samples. If you want to draw it, so 80 plus 60 is how much? 140 plus 40, 180 plus 20, 200. But here, this, though you have 200 data is 200 values are there, right? 200 counts are there. You're taking only 20. So this population or this segment you are underrepresenting. Okay, if you literally go by the proportion, right? So on a case-to-case basis, you need to determine the proportion of the data also. So it is not necessarily always the sample should be the same proportion as the population. So now we understood the difference between the simple random sampling. Though it is unbiased, it is not, there is no coverage. There could be chances it will not cover all the segment, whereas stratified random sampling is unbiased and it coverage. So we can see the coverage here, and also we need to make sure that we are going to if every group is represented proportionally to its relative size in population, then you can go for the same. Your sample should have the same proportions as that of your population. Sometimes if it is not, if it is disproportional, right, so need not to literally go by the so this same proportion of your population while you sample the data. So it is unbiased and it is representative of the population. It covers every segment. So what is the disadvantages? It's a time consuming activity. You need to identify all the segments. Okay, if you miss out any one of the segments, you are gone. But the advantage is obviously the high degree of representation of all this data or layers in the population. All right, next one is the cluster sampling. Cluster sampling is somewhat similar to the stratified random sampling, but there is a difference here. So even in the case of cluster sampling, we divide the entire population data into segments, which are nothing but the clusters. Okay, but in the case of cluster sampling, what we do is, for example, this is my population. So what we do is we divide this into multiple segments, or the clusters. Each cluster is a group. Is a 1, 2, 3, 4, 5, something like that. This is a classic example. Let's assume that you want to evaluate the earnings of airport staff in the United Kingdom. Let's say there are 400 airports are there in United Kingdom itself. We just think that way. And each employee represent clusters, and we randomly select 40 airports, and 40 airports represent the primary data. Okay, so or else what we do is we group each and every airport as a cluster. Okay, cluster. Randomly we select few clusters, 1, 3, and 5. 1, 3, 5. Randomly we collect we sample the clusters. We select the clusters. First we do the cluster segments, because this is airport 1, 2, 3, 4, 5, and then randomly we select the clusters 1 and 3 and 5. We select it. So this is 3, and forget about this is 5, right? So 1, this is 1 and 3 and 5. So what we do is we randomly select the clusters, and we are going to consider all the staffs that work in each airport of 135. Randomly sample the clusters. Okay, let's say you have 10 clusters. Of the 10 clusters, randomly you select 3 or 4 clusters. And then what you do is, in the 4 clusters, you run a survey with all the staffs. I'll give you another example. For example, let's say you go to you booked a hotel in a holy place. Okay, let's say you wants to go to Rishikesh, right? A specific or Rishikesh, right? You want to go to Rishikesh on a specific season only, they will open it, right? So that time you booked a hotel, or let's say in South India, right? We have something called Kumbhakonam temple. It's a very popular temple. There is something called Mahamaham. It's a very important event. So there is a tradition that all the gods come and take a bath in the Kumbhakonam temple, the well. Okay, so that is what it's a Mahamaham. So what people know very well, Mahamaham is happening on a specific day. They book it. They book the rooms well in advance, at least 2 months in advance. They book it everything. Let's say as a hotel owner, you offer complimentary breakfast for all the people those stay in your hotel. So what you do is, on that specific day, people come and they go to temple, they take their dip in the well, and then they come back, and morning they come and have their breakfast. So what you are doing is, you want to understand the customer's sentiment about the free complimentary breakfast which you gave it to your customers, the taste. Okay, so based on which you want to decide whether you can retain the existing caterer or you want to change the caterer. So what you do is, each floor you have close to 20 rooms are there. Okay, and what you're doing, randomly select 1 or 2 rooms, 2 floors, and then you ask your staffs to run a survey with all the people they live in floor number 1 and 5. Okay, let's say you have 20 floors are there. Each and every floor, you don't have to go randomly 1, 5, and 7. 3 floors. That is 3 floors, or each floor is a cluster. You just think that way. And what you do is, very well, each floor, the mix of people from across the India, they stay there. So in that case, 1, 3, 7, if you take only 3 clusters, 3 floors, and randomly, and if you send your people to run a survey with all the people in those 3 floors, you will get to know, because you are very clear in those 3 floors. There is a 100% chance or 90% chance all the state people mix on or staying there, right? So if you send it there, you will get to know their feedback, based on which you don't have to run a survey with all the 20 floor people. It's a time consuming. You need more staffs. Instead, you cluster it. So 1, 3, 5 floors. Right. So that is what your cluster sampling. Sampling techniques to avoid convenience sampling and judgment as sampling. This is not always right, good one. We rarely use this technique, convenience sampling, all these things. Okay. Next, we will jump into something else called the, just give me a second here. I'm getting a call. Just give me a second. Recording. So next we'll take a look at the central limit theorem. So if the sample size is 30 or more, the sampling distribution is going to be approximately normal distribution irrespective of the population distribution. What do you mean by this? Let's take a look at these three population. So three different type of population. So let's, in this population, I could see it's a uniform distribution. It's a bimodal distribution. In this population, the population data distribution itself right skewed. What central limits theorem says is, when you draw samples closer to 30, right? Or 30, when you draw samples irrespective of the type of the distribution of the population, it will become approximately normally distributed. See, 30 or more. Okay, so when you draw 30 and above, it will become normally distributed. And also the sampling distribution of the means is somewhat bell-shaped. Okay, so that is also the one of the properties of this one says. And for example, you are drawing 3 or 4 samples, and if you plot each sample's means, right? If it is, so if that is going to be bell-shaped, okay, the sampling distribution of the means is somewhat bell-shaped. Okay, and the another property of the central limit theorem. So now you understood central limit theorem property one. What it says is, irrespective of the type of the distribution of your population, when you draw sample 30 or more, it will become approximately normally distributed. And the second thing, what you need to do, remember is, sufficient large sample distribution of sample means will approximately equal to the population mean. The samples distribution of the samples mean will approximately equal to the population mean. So this is also one of the important thing you need to remember it. I'll just show you with some data so that you should be able to understand. Let us assume that in my population, I have 1, 2, 3, 4. Only 4 values are there. What is mu here? Mu stands for this population mean. So in my population, I have only 4 values are there. You just think that way, okay? What is the mean value here? Average value of this one? 7, 8, 9, 10, right? So, 7 plus 3, 10. 10 divided by 4 is 2.5. This is my population mean. If I randomly sample data with replacement, for example, 1, 1, what is the maximum possible number of samples I can draw with each sample with size 2 with replacement? 1, 1, 1, 2, 1, 3, 1, 4, right? So what is the average here? This sample average, sample 1 is average 1, 1.3, 1.5, 4, 2, and 1, 4, how much? 2.5, right? And similarly, so 2, 1, 2, 2, 2, 3, and 2, 4, and 3, 1, 3, 2, 3, 3, 3, 4, and 4, 1, 4, 2, 4, 3, and 4, 4. If these are called your samples mean, okay? And the sampling distribution of the sample mean, this is the distribution of these samples means, okay? For example, here 3, 1.5, here 2, and 5 is 2.5, the average 6, 3, right? So all these values are called the distribution of your sample means. The distribution of the sample means. When you take a mean of all these means, it will approximately equivalent to your population. It will become 2 point. You will get 2.5 only. You can try it out. So 3 and 3 plus 1 is 4, 2, right? So 2.5 and 3 and 7 is how much? 3.5. And here 5, 2.5. And here 6, 3 and 4 is 2 and 8 is 4. Okay. If you add all these values, how much you get? Can someone help me out? So 1.5 or 2.5, 3, 4, 5, 7, right? Here 7, and how much you get here? 3, 4, 6, 7, and here how much? 3.5 and 2.5, 4, 5, 6, 7, 8, 9, 10, 11, and here how much you get? 5 plus 4, 9, 10.5. Is this correct? I think something wrong here. So 1 is 1, 3 is 1.5, 2, and 2.5. So here, how many samples means we are getting it? So 4 plus 4, 8, 16, right? In the numerator, 16 should come here. And here something wrong. 5 is 2.5. 6 is 3 and 7 is, yeah, something wrong. Here 7, right? 7 means how much? 2.5. No, 7 divided by 2, 3.5. 3.5. Here 8 divided by 2 is 4. So here how much you get? 3.5 and 4, 5, 6, 10, 13, right? 24 plus 14, how much? 24 plus 14, 8, 38. 2.5 something, right? So that is what it says. The sample, see the sampling distributions of the sample means will approximately equivalent to your population mean. So your population mean is 2.5 is equivalent to the sampling distribution mean is also equivalent to 2.5. Somewhere I made a mistake. Somewhere it will come 2.5. It will come exactly, sorry, 2 16s or 32, right? 32. And how much? 6. Yeah. Yeah, 2.5, correct only, right? 2.5. Yes. The sampling distribution of the sample means, see, you need to plot all these means. Okay, you need to add all these samples means and then take the overall sample. So 16 sample, right? So the sampling distribution of the sample means will approximately equal to the population mean. This is also you need to remember. The first one is when you draw a sample close to 30, it will become approximately normal, irrespective of the type of the distribution of your population. The second property is the sampling division of the sample mean is equivalent to the approximately equal to the population mean. Very simple, right? And that's all. If you remember this one, that is more than sufficient. And like how we can find out the standard deviation for a population and for a sample standard deviation small s and population, even for the sampling distribution, also we can find out the standard deviation, that is called as sigma divided by square root of n. So this is called the standard error, SC, standard. How far? See, what we are doing is how far this mean is different from the population mean, right? How far each mean is different from how far each mean is from your population. This is somewhat closer. This is 0.5 something else. So to find, this is called a standard error. How far each mean is away from your population mean, that is what your standard error. So for that, sigma divided by square root of n. You need to take the square root of your population size, sample size. So population standard deviation divided by square root of n. This is the one will give you the standard error. Very simple to remember, right? The next one is you need to keep these two. So there are two things that you need to remember. We never actually create a sampling distribution that would require a huge effort. So look here, even in this case, we just took only 4 values, right? Even for these 4 values, to create a sampling distribution, it's a huge effort, right? 16 samples we were able to draw for the 4 values. But hence, right, we never actually create a sampling distribution that require a huge effort, since we cannot afford to make samples, multiple samples. What we do is, we based on a single sample, you will have to make inference about the population mean salary. This is where tools like confidence interval estimation, and this is where, see what, it is really painstaking process, right? So you need to create a sampling distribution, right? It takes a lot of time. And instead take a single sample. With that single sample, is it possible to make an inference about my population mean salary? Because that is where we have something called confidence interval and Ipath testing. These are the 2 other techniques that are available. Next, we will take a look at the confidence the confidence interval. Okay, what is confidence interval? It's a very simple and straightforward one, the confidence interval, but we need to remember this formula a little bit. Okay, that's all. Otherwise, it is a very simple one. I just go and okay, so confidence interval. To study a population of interest, it is common practice to take a sample and use the results to draw a conclusion about its population. That is what we discussed it. Suppose I wanted to estimate the average age of students at a college. So I choose a random sample. Okay, so this is my college. All the students are there. And I took a random sample of, I ran a survey with few students. By running a survey with a few students, I got to know that the average age of the students is 23. Let's say in a college, 5,000 students are studying. It's a very big college. The final year students, BE final year students, right? All the engineering students put together in the final year, let's assume that 1,000 students are there. I ran a survey with 20 students. With that survey, I was able to conclude the average mean age is 23 for that 20 students. With that, can I say all the final year students average age is 23? See, okay, here I'll make it very clear. My sample, right? I ran a survey with 20 final year B students. The average age is, as per my sample, it comes around 23. So does that mean all the final year students average is going to be 23? Can I generalize it? So what I came up here is called my point estimate of the population. We do not know the population average age. All the final year B students average age, we do not know the population mean. We are making an estimate based on the sample. I ran a survey with 20 final year B students. And as per that sample, it comes around the average age is 33. This I call as a point estimate. It's a single value. This I computed from my sample. Okay. So in this case, my population mean is, I don't know. The sample was only a selection of students from the population. It will never be a perfect representation of the population. Got it? So for example, if I run a survey with another 20 students, let's say, I ran a survey with 20 final year students, and I spoke to each and every guy, I got their age randomly. Okay, and so let's say now you are doing one thing. So what you are doing is you are challenging, it cannot be average age, cannot be 23. for all the students. I will run another survey with other randomly sampled 20 guys. According to his sample 22. According to, these other guys sample 21. Sample to sample, the age is varying. Since variability is there, these estimates, since variabilities are there from one sample to another, we quantify the uncertainty using confidence intervals due to the variance. Now the question is, can I see this, person Prakash ran a survey with 20 people, Rajesh ran a survey with 20 people, final year people, and this Mahesh, he ran a survey with final year students, 20 students. All the sample size are same, and it's a random sample, but sample to sample, the average age is differing. So what can I do? So, this is called your sampling error. Sample to sample, the mean is differing. This is called your sampling error. So, so in this case, we have some kind of uncertainty. Now we got confused. Okay, can I say all the final year students average is 21 or 22 or 23? I got confused. There is a degree of uncertainty. To address this degree of uncertainty, there is something called confidence interval is coming into picture. Okay, the confidence intervals are something like your limit. You will define some lower bound, upper bound. Supposing, let's say, your manager is very simple analogy. Your manager is very, very strict. Okay, and he wants you to be at office every day by 9:30 a.m. sharp. Okay, and what you are doing is tonight you are working late in the night because of some other period. Even your manager asked you to stay late and complete certain things. You did it. And tonight is asking your manager, man, you stayed late tonight. So what time can I expect you tomorrow? You know very well about him. He expect you to be there at office by 9:30. So can you say 9:30 or can you say 10:30 since you stayed late tonight? Or can you say 9 a.m. or 9:15 a.m.? You're a smart guy. You simply say, instead of saying a point estimate, giving a point, sir, I'll come here exactly by 9:30. Instead of saying that way, sir, I will make it anywhere between 9 to 10:30. So that, or you can say, 9:30 to 10:30. Because I stayed late, anywhere between 9:30 to 10:30. I'll try to make it 10:30, 9:30. In the worst case, I will be available anywhere between 9:30 to 10:30. So that even if you go by 10:25 a.m., you will not question. You can still go ahead and say, hey, wait, 9:30 to 10:30 I told, right? 9:25, 10:25 he came here. You are defining a range of value so that you are smart. So most of the guys, they say something like that. So if you ask the money, right, what is the painting cost to paint the whole apartment? How much will it cost? They'll give you the rough estimate with some range of values, anywhere between this. They never say the exact value. Smart guys, right? So, okay. So confidence intervals provide us with a range in which population is likely to fall. So here in this case, so one guy is getting the sample mean is 21, 21, 22, 23. So now the population mean can fall anywhere between 21.5 to 24.5. Between 9:30 to 10:30, my population mean can fall anytime. So I might, on an average, right, if I go home every day late by 4 hours, or on an average, what we say, right, between every day between 9:30 to 10:30, anytime I may come to office. So the population mean, this is your population mean, falls anywhere between these two values. Now your question is, how do I define the lower bound, upper bound? There is a formula for this. Let us not worry about this. And the next one is, okay, if you say your manager, I will come tomorrow anywhere between 9:30 to 10:30, you are telling him. Now he's asking another question. How confident are you that you can make it between 9:30 to 10:30? What you gave him was the range of values, confidence interval. Now you want to know the confidence. How confident are you that at least you come between 9:30 to 10:30? There could be chances you might not be able to make it even by 10:30, right? because 9:30, 10:30 is a peak time. Heavy traffic will be there, right? So that is when we have something called confidence. And if you look at this distribution here, so here I've drawn a line. Here I have drawn a line. This is my confidence interval. So, or let's the overall the area under the curve is 1. Please remember, always the area under the curve is 1. Normal distribution, always the area under the curve is 1. Okay. So in this case, you are defining the boundary, right? So 0.025 on this left side, 0.0. So there is a 0.5 probability that you cannot make it on time. So which means there is a 0.95. One is the total area under the curve. That is what I mentioned. 1 minus alpha. Alpha is 0.05. Most of the time, in statistics, the researchers, they use the value or they choose the value for alpha is 0.05. What is alpha is? Alpha is level of significance. Okay, level of significance. Or so 1 minus alpha is 0.05, hence it is going to be 0.95, which is nothing but 95% confidence. There is a 95% confidence that I can come to office tomorrow between 9:30 to 10:30 p.m. So what about the remaining 5%? There is a chances that I may not be able to come early, or I may not be able to come later also, right? So for example, so this is the thing, okay, and 95% confidence. Okay, you just think this way. Yeah, okay. So it is something like that. So there is a plus or minus here, right? So alpha equal to 0.05. We need to do a lookup on some table also. You remember in school time, the back of our math book, we found something like that, right? Table, z-score table and all. We need to look at that one. You just think this way, okay? From the analogy point of view, 95% of the time, I should be able to come anywhere between 9:30 a.m. to 10:30 a.m. There is a point, there is a 5% chances that I cannot make it even this time. Okay. So that is what it says. So confidence, the amount of certainty we have when we estimate a parameter. So we estimate a parameter based on the range of values. That is called your confidence interval. So if somebody is asking you how confident are you with this confidence interval, right? So for this one, a confidence in a range of values that is likely to contain unknown population parameter. If you draw a random sample many times, your certain percentage of confidence will contain a population mean, certain the percentage of confidence. Confidence limits are the numbers of the lower and upper end of a confidence interval. See, this is what. If you draw multiple samples, take for example, in the case of students' age, right? All the final year student, sample one, the confidence interval is 21 to 23. And let's say sample 2, as per the sample 2, you ran a selection of Prakash ran a sample. As per him, the lower bound, upper bound is differing. 21.5 to 24. And this guy, okay, so let's say another guy. Sample to sample, the confidence interval also changes. Now it is time to help you to understand what formula that we use it to compute the confidence interval, lower bound and upper bound value. So that, look here, this is the formula that we use it to find out the confidence interval. This is my X bar, sample mean. Okay, let's say my sample mean here. Did I put any value here? Yeah, my confidence, my mean is 22. My sample mean is 22. Okay, you need to find out the for the lower bound, what is the confidence interval. See, so you need to define the range of values, two range of values, right? For example, 21 to 23. The average edge can be, the population mean can fall anywhere between 21 to 23. Okay, somewhere it is falling it. So there is a 95% confidence that the average age of the all the final year student age fall anywhere between 21 to 23. There is a 95% confidence. So here, how did you arrive 21? So you have taken, as per your sample, the mean is 22 plus 1.6 z alpha divided by 2. This is a constant value. Okay, into your population standard deviation is square root of 100. Let's 100 students, you ran a survey, square root of 100. And this is, you just think this is your population standard deviation 2. And upper bound, you arrived with this value, and lower bound, you got this. So anywhere between 21.6 to 22.4. As per this, now you understood, this is the formula that you need to use it. X bar is your sample mean. Your sample mean is 22 plus or minus. Okay, so plus is upper bound, minus is your lower bound. This value is 1.96. Don't ask me why and all. Okay, you don't blindly think it's a constant value. Into your population standard deviation, as per this, you are getting 2. Okay, and 2 divided by square root of total number of students, 100. Okay, 2 divided, so this is 10, right? So 2 divided by 10 is 0.2. Into this one, you'll get 22.4. So lower bound. So here we say 95% confident the population mean can fall anywhere between these two. This 1.96 is something like your, okay, so this portion is called margin of error. Okay, if you multiply the z value into sigma division, you will get margin of error is the maximum expected difference between the true population parameter and sample estimate of the parameter. So that is what the thing, margin of error is 0.392. So this is the difference between the true population, the actual population parameter, the sample parameter of that parameter. Okay. So that's what margin of error is meaningful only when stated in terms of the probability. It's a confidence level. That is what 95% confident the population mean can fall anywhere between 21.5 to 24.5. So for our example, for a large sample, the truth is 90% critical value 2.1. So the standard is okay. 1.95, right? So 1.95 is something like this. Okay, that we will see tomorrow. So at this moment, you just think this way. Okay, upper bound, lower bound. So this is the one. Okay, the 21.6 and 22.4. And here, your 95% the population mean is between 21.6. So this is the confidence interval. Okay, the next one is, look here. I just go back here. Yeah, this is what. Let's say I have taken 20 samples. Sample to sample, the mean will vary. Since the mean varies, obviously the lower bound, upper bound will also change, isn't it? As per this formula, if the mean is 21 year, obviously this value, upper bound, lower bound will change, right? Let's say I draw 20 sample. Each sample's mean vary from one sample to another sample. So here, we can generalize like this. Let's say I have 20 samples, right? 95% of all samples means are here. There is a 5% chance that the remaining 5% of, so out of 20 sample, 19 sample. Okay, 95% of 20 is how much? 19. So out of the 20 sample drawn, 19 samples means fall anywhere between this value. So mean anywhere between, so this is one sample. This samples, I mean, a lower bound, upper bound. See, sample to sample, the lower bound, upper bound also changes, right? So there is a 90% confidence level that out of 20 samples, 19 samples contains population mean. So this is somewhat, it is all falling somewhere here, right? That is what it says. So what is the Z? Z is the critical value, which is a cutoff value that tells us how far from the sample mean we can vary. Very simple one. The next one is to summarize. Confidence interval is a range of values that is likely to contain the unknown population parameter. So we do not know the population average age. With the help of confidence interval, we can define the range of values. With that range of values, we can say that range of values will likely to contain the population parameter. Parameter is nothing but population mean or population standard deviation. You remember this. If you draw a random sample many times, a certain percent of confidence intervals will contain the population mean. This percent is the confidence level. Certain percent of the confidence interval. You remember, out of the 20 samples, 19 samples contains the population mean. So 95%, right? 95% of the 95% confidence is out of the 20 samples, 19 samples, the confidence interval will contain the population mean. Confidence limits are the numbers at the upper and lower end of the confidence interval. Margin of it's a confidence interval. In a confidence, the range of values above and below the sample size is the margin of error. So the lower bound, upper bound, right? So when you use plus or minus, we can find out the margin of error is very much helpful in that kind of situation. So if you remember this simple the analogy, that is more than sufficient. Okay, sample to sample, obviously the mean will vary. Since the mean varies, the confidence interval for each sample also varies. The lower bound, upper bound also varies. Okay, and what is confidence level? Using confidence level, we can tell what is. Okay, now the question is, sir, can I, instead of saying 95%, can I say 99%? Okay, and can I say 90%? Because I'm not so confident. Okay, see, saying 90%, you're not so confident. If you say you're overconfidence, if you say 99%, you're overconfidence, you are underconfidence. Hence, most of the time we use 95%. Okay, 95% only. Now the question is it possible for me to say 99%? My manager is asking me, can I say 99% confidence level? So in that case, right, the Z value will vary. This value will vary from 90% confidence, it will be different. For 95, 99%, it will be different. So higher the confidence, if you have to give, this one will become very wide. Which one? 21.5 to 24.5. You will have to say like this. See, simple here. 9:30 a.m. to 10:30 a.m. You are 95% confident. If he asks you, can you tell me 99% confident? So what you will obviously will say 9:30 to 11, sir. I'm 99% confident. The range, the interval range vary. In the range of the interval, right? Interval range is wide here as you increase the confidence level. If he says 90%, so 90% you can say, right? So I can say 9 a.m. to 10:30 a.m. I can go 90%, but I'm 90% confident. I cannot assure you, sir. 90% only. 95% confident. 9:30 to 99. So 9. So because he is very particular about this confidence level. 90. So then what you're saying is increase the range. 9:30 to 11. 11 I can come. Even if there is a traffic condition, some politicians are coming here, any riots, right? So I can make it anywhere between 9:30 to 11, sir. So as the confidence level increases, the range also widens. Okay, got it? And here 90% also you can say 9 a.m. to 10 a.m. you can come, but I told you only 90% is confident, right? Remaining 10%, which means the remaining 10% I cannot make it. Pretty straightforward. If you use this analogy, you should be able to understand this one. So we have covered so far the confidence. We started with the inferential statistics, and we discussed about the difference between descriptive and inferential statistics. And then we discussed about the different types of sampling technique, and sampling distribution also we discussed, and followed by we discussed about the central limit theorem. And as per the central limit theorem, we discussed about two properties. One is as the sample size approaches close to 30, the distribution becomes normal, irrespective of the type of the distribution of your population. And then second property is the sampling, the distribution of the sample means is equivalent to your population mean. And finally, we discussed about the confidence interval and then confidence level. Any questions so far? What is tomorrow's topic? Tomorrow we will continue with the hypothesis testing directly. Okay. Probability, I will take it up later, because if I start probability, you will feel, you will feel, bit difficult. So hence we will jump directly into the hypothesis testing and see if I can complete it tomorrow. If I can complete it tomorrow, right? We will start the machine learning part next weekend itself. Or yeah, next weekend, what I will do is I will conduct all these tests like hypothesis type, hypothesis test and independent t-test, z-test, two sample independent t-test, all the things, right? I will conduct it in Python, and then we will jump into machine learning part. Fine. Any questions so far? Okay, since you don't have any questions, I'm going to wrap up the session now. See you tomorrow, same time, 4:30 p.m. Okay.